Okay, the record is on, so we'll come back to class. But let's go over this a little bit. Okay, you guys are gonna have the class on Mondays and Tuesdays. Monday, hopefully it's gonna be about the lecture, and then Tuesday we're gonna have the design lab. Except the first Tuesday, we may not be quick enough to start the design lab yet, so it's just gonna be another lecture on Tuesday, so that we can finish this off very quickly. Okay, and all right, so that's it. So this is today, the 17th, and then the 18th we're gonna have the lecture on tension members, and then from then on it's gonna be one lecture and then one design lab. Okay, and everything should go according to this schedule. Please notice that I don't have the reading week break for you guys. Maybe it just fits just like that, so there's no room. However, please notice that in this week, and remember this, I tell you in the very first week that here, this lecture about beam not laterally supported generally is for the final exam. Okay, but Asd Sutat always says that for the sake of continuity, because I am assigned to instruct about the beam laterally supported, so it's only appropriate that I should take care of this. So he wants me to always make notes on this one. Okay, and then we're gonna have the midterm exam, and then my part is over. And let me tell you one more thing. I believe that this is going to be my last CVE341. Okay, so for those of you who somehow will decide to drop the class or couldn't get past it in this attempt, next time you're taking this one, you're gonna be instructed by Asd Sutat alone. It used to be that way until he became the head of the department. Then this semester he's supposed to get 100% back, but then there is a special request from SIIT, so he and I decided to answer the call because our students have been taking their classes for some time now. So when they ask for a favor, I think it's only appropriate that we return it. So that's why we are teaching like steel design classes 2 times this semester. So we decided to split the load 50-50 as before. Okay, so that's why I am still teaching this one, but I don't think it's going to happen this time next year. Okay, so that's it. I'm glad that I don't have to go over this again in details, because this is not the first time we are using this anymore. Some of you guys should be familiar with this, and all of you should be familiar with the structure that I use for grading. So the small details change, but the way that we do things are the same. So if you want to know how well you're gonna do in the homework and the exam, everything is based on this rubric structure. Okay, and you should see that in this class you must be able to perform structural analysis. It's there on the beginning of every ability, because this is a design class. Okay, and I will talk about the very sacred concept of design later. But when you are going to do some design, or when you are going to design something, you always have to know the forces or load acting on your structure. And with that, I mean the internal forces. So that, in short, you have to be able to perform structural analysis. So for those of you, when you hear the word structural analysis and then you shrink, you squeak, or something like that, you know that there is no getting away from it, because this is the structural engineering class. We are going to design structure by using the material that we call steel. So you must know the forces acting on your members. So this is the essentially is the part that you have to be able to do. Okay, and you need to be able to identify the materials that you're going to use and the design concept. We'll talk about that shortly. So if you fail to get through this, and this one more, you must be able to identify how many ways your structure or your members are going to fail under a particular loading condition. For example, if you have the member under tensile force like this, how many ways can the tensile force cause a failure to your member? If you can identify all the ways that they can fail, your structures can fail, you're up to the necessary level, that is the F level. Okay, I mean, if this is what you can do, you're just going to be right there at the threshold. And to perform beyond this, you need to, pass all these three. If you don't get the first three level right, you're not going to get to that. See, that's a prerequisite. Okay, and the major chunk of this is the calculation force, and then you are going to have the 10% head off in the summary. And maybe in the future I need to change this, but I have to say that I have been pretty kind, because in the real world, none of the first 90% would matter if you cannot summarize what you are going to do in your real work, right? Because in the end, in step number 5 is when you will tell the construction, or you will tell the draftsman, okay, this is the member that I'm going to use. This is the size that we are going to erect for the structure. Okay, so in fact, the step number 5 is the most important thing. But I kind of think that you are still a junior engineer to my eyes. So we may let you go a little bit lightly if you cannot summarize it. Hopefully you can polish this, after the exams and so and so. So yeah, we still focus primarily on your ability to calculate the stuff. But if you think of yourself as an engineer and you want to do well, you must be able to know how to summarize things. Okay, and then the 6th level here is a special thing. It is awarded to someone who, say, can do things beyond the call of duty. So if you play the game Call of Duty, that's what I mean. For example, you demonstrate that you have good engineering judgment by selecting the lightest member and therefore the most economical one, and something like that. Okay, and the template is pretty similar to all other aspects of design. So we are okay with this one, I hope. All right, so let me start off now. I am aware of the fact that we missed one, say, the introductory package of the class where I give you the percentage and so, because we used to give 60% on work because it's the online classroom and stuff like that. We may stick to the same thing, but I cannot say that for sure just now because I have to talk to Ajahn Sutat. This is for trying to help students. And ladies and gentlemen, this is a design class. This is professional class. What you all do in this class can be used in your career. So I would really expect you to do your own work for your own future. If you can do this class very well, it means that you are almost ready to go out and work and design some steel structure. Okay, so you better try to do it yourself to your best ability. Just ditch your whole idea of trying to get the initiative from your friends, because when we talk about design, when you are going to design something, that means that thing never exists, right? if you are going to design something, it means that that thing never really actually exists. The architects will give you the drawings of the building, and then you have to make it happen by designing the sizes of the columns, the beams, the floor, the foundation, the roofs, and so on. So at the beginning, it's fair to say that nobody knows. Okay, nobody knows what the sizes of the building is going to be in terms of the members. So you begin from nothing, you begin from scratch. You begin by looking at the empty paper and trying to use your engineering knowledge and your calculation to come up with something. So that's why design, you can say, is the ultimate, the engineering knowledge, because you are now asked to conjure something out of nothing by using the knowledge. So if you cannot do it now, chances are, you may not have the initiative for yourself to do it in the future, because you never care to develop one. You just want to take the initiative from your friend. Okay. So when we design something, there are always two sides of things. On the left side, we should have the demand. Okay. So the demand in this case would be the load, right? Forces, so to speak. So you need to know how big the force is that your structure must carry. And generally, we have so many kinds of load. The date load, that's pretty simple, right? It's the weight of the structure. It's the weight of the floor and stuff, all kinds of things. But this can be calculated. But the next one, it's a live load. How much do you know about it? The live load is something that tells you how you are going to use your building. So we can say that a live load, when we talk about occupancy, how the building is going to be used. Okay, and generally this is the most important part, because this should use red for the dramatic effect. Part generally is governed by law. So, okay, that means we involve law. That is why we have the license. We need to have the license in order to work as an engineer, because we need to know the law, and we need to make sure that our building will, be designed and constructed according to the law. So that means before you begin to do anything, you must know the law here. And you must make sure that you use the live load stated by the law in your design. For example, if you are going to design the school, you must check how much the law says that the live load would be for the structure of the school. The structure must be able to carry at least that much load. However, keep in mind that when the law says a number, you need to make sure that your structure must survive that. But if you think that the number given by the law is too low, you must use your proper engineering judgment to increase it. You as an engineer must take full responsibility of the number you use for the design. Even though the law says this is the minimum number that you should use, but if you feel like that number is not enough in some cases, you must know it and use the proper number by your own judgment. Okay, so now there are a few more things coming off this. So yeah, there are more load, and the law would say, okay, calculate the earthquake force by using this standard, the wind load by using this standard, and so on and so forth. And there's a law about the load combination and stuff as well. Okay, so when you know the load, you put the load on your structure, right? Your job is to provide the structure for the building. It doesn't have to be the building, but this concept is for everything that you do as a civil engineer. It could be foundation, it could be piles, it could be dam, it could be road, it could be anything. But for the fact that I am a structural engineer, so I tend to use the word structure like all the time. But what I'm saying is that it doesn't have to be structure. The design concept is applicable to anything that you would do in the future. Okay, so once you know the load, you analyze how much the forces your structure have to carry, and then you make sure that the demand is met by the supply. Okay, and supply here, you can say it's a resistance. We are going to predict how much our structure is going to be able to resist. Okay, so in trying to, now the key word here is to use the word predict. Because this is a real thing. Nobody knows what's going to happen in the real world. How can you say one piece of member is going to take this and that much force exactly? We never know. So what we can do at best is to predict the strength of our member. Okay, and generally what we can use to predict would be, from the help of the formulas in AISC, AISC specification, which I don't know if I posted, but I believe I did. Right now we up to year of 2016, I believe. Okay, you can use the guidelines and the formulas provided by AIC spec to predict the strength of your structure. And in this case, we of course talking about the steel structure because we are in the steel design class. Okay, or you could use some other things or specs or standards. Okay, such as EIT. Thankfully, we folks at EIT have been able to say almost finalize the new spec for Thai engineers. But I have to say that that is actually based on AIC spec. Okay, so but one more thing that you need to know is that in Thailand, because of the laws and stuff, you cannot use the word spec or something. It has to be standard. Okay, so when we talk about the guideline for steel design in Thailand, you can call it EIT standard. But when you go work with foreigners, when you talk about AISC, please remember that AISC is not standard; it is specification. So please call them by the correct name. Be proper engineers. Okay, use the correct names. Now, why do I say predict? Now, the important thing here is that this right side here, this is not the law, which implies that if you don't believe in them, you don't have to follow them. Okay, this is on the left side, the demand is the law. You as engineers must provide the structure strong enough to withstand the load as stated by the law. This is a must. Okay, but on the right side, how are you going to predict the structure strength? It doesn't matter how. The law doesn't really say which method that you can use. So, you're free to do whatever you want on the right side. If you think you're better than folks who write these stuff, you can use your own stuff. Yes, but if nothing bad happens, you're fine. But if something bad happens, they ask you, hey, how do you predict the strength of your structure? I say, oh, I use the result from my own lab at the backyard of my home. It doesn't bode well for you, because the guys who write this stuff, they are very, 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 very good. So most of the time they are correct, but that doesn't mean that they can cover everything in the world. From time to time, you may run into the work that creates some new stuff, that the new ground that hasn't been covered by, you know, the content in here at all. So then you're gonna have to use your proper engineering judgment and do things to your best ability. So on the left is absolutely necessary and especially important to know that, okay, let's say if you are going to work in China, for example, you must know what laws they use over there. There are no excuses that you don't know at the beginning that, okay, the law states that the building must be able to do this and this and this and blah, blah, blah. So the demand side is very, 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 very important. How you are going to predict the strength of your structure to meet the left side, you have a freedom to do something yourself, but you know, just like Spider-Man, right? Freedom comes with responsibility. So you must know how to properly predict the strength of your structure. Okay, so let me move over a little bit here, because I always start the class like this. The predicted strength is, in fact, the strength of your structure by calculation, based on calculation. Okay, let me call that with an R. So the strength based on calculation, or the predicted strength, we call it nominal strength. You can say it's N, okay? This is based on calculation. Or you can say prediction or predicted strength. Okay, so let me ask you guys, is it a good idea to use the predicted strength to design the structure? The example I used on Friday is that if you know that your car weighs about 1.5 tons, okay, and you have a nail, one nail that can take tensile force equal to 1.5 tons. So let's say if you can hang your car safely, you know, by attaching something onto the nail, your car weighs exactly the same as the tensile force that the nail can carry. Would you like to hang your car with that nail? Oh, yes. Please, the guys. Well, the semester is back on. Are you all falling asleep? Hello? Hey, anyone?
Hello.
Thank you. Just one? Not for it, right? Anyone else?
Hello.
Thank you. Can I have more, please? Come on, wake up, guys.
Morning.
Morning. But is it a yes or no?
Yes.
Yeah. Please answer my question. Would you like to hang your car on the nail that to carry exactly the same as your car's weight? No. Thank you. Finally, wake up. This is what you will earn. This is what you will use to earn your living as an engineer, you know? All right, so the answer is no. So that means we cannot use the nominal strength to design our structure. We must incorporate something to make our structure safe and turn this into what we call design strength. Okay, so there are two different words that you need to understand now. Nominal strength is the absolute maximum strength of your structure. You can say is as good as it gets. It cannot take more than this. Okay, but you cannot use that nominal strength, the calculated strength, the predicted strength to design the structure right away because it's not safe. You need to turn that number into what we call the design strength by using what we call this omega is factor of safety, or phi, this is reduction factor. Okay, so let's say I have the nail now, but instead of saying the nominal tensile strength of the nail is 1.5 tons, I say the design strength of the nail is 1.5 tons. Now that's a major difference. If I say the design strength of the nail is 1.5 tons, it means that that nail can actually take more than 1.5 tons. Let's say, for example, if I have factor of safety equal to 2. If my factor of safety is equal to 2, and I say the design strength of the nail is 1.5 tons, it means that the nominal strength of the nail is actually 3 tons. So now if your car weighs 1.5 tons, you can hang your car safely on that nail, knowing that you have a long way to go before the nail will actually fail. So any question? Do you grasp the first concept? This is how we apply the factor of safety to the design. Any question, folks? No? Oh, I wrote in the last page. One thing. Can I move it? I'll do it later. You always forget. Anyway, okay. Anyway, I want you to see this page, so I'm just gonna add one after. Okay. So now you understand the concept of the demand and supply, right? And now you understand the concept of nominal and design strength. Now, when you look back here, it's simple enough to see that you always make sure that your supply is greater or equal to the demand, right? So now we're gonna look into more details about the demand and supply. Now on the demand side, we know it's a low. But right now for the steel design, we have two design philosophy. We can just take the load as it is and combine them without doing anything. That is called the service load. Okay, and we are going to design by comparing the forces occurred caused by the service load to the nominal strength of the structure divided by factor of safety. Now remember that this has to be always larger or equal to that. Okay, This design philosophy is ASD, coming from allowable strength design. Okay, we use what we call the service load. So the key word here is the service. Service load is the load as it is. Okay, you combine them, date load, live load, and so and so, and then you compare with the nominal strength divided by factor of safety. So this becomes your design strength. This is ASD. Another one, instead of use service load, we increase the load to account for some uncertainties that you never know. For example, the live load could be more than what the number suggests. The floor could be thicker than you actually cast the concrete for, and so and so. So we increase the load due to some uncertainty, so we call that factored load. Okay, now you will, because you increase the load, you expect to use the actual load, but you account for some uncertainty. So you are going to compare this with the nominal. It's like you use almost everything you got, but reduce it by the reduction factor to also account for some uncertainty, such as if you are going to use the steel hot roll beam, is it actually manufactured to the size that they say? Or are all the formulas that we use actually correct? Or something like that. So we are going to use the full strength of our members, but we're going to reduce it a little bit to account for some uncertainty by the reduction factor as well. Okay, so the key word here is a factored load. Your load will be increased by the factors. You compare with the design strength, which is reduced by the reduction factor. This is the factor of safety. And so this is another philosophy. It is called LRFD, the load and resistance factor design. LRFD. Okay, now listen very carefully from now on. In our country, we have on the demand side our law that is called Building Act. I don't remember the number. Or กฎกระทรวง. All right. Now, in the current Building Act, for steel design, there is only ASD load suggestion available. LRFD is not available. They ignore it, they don't understand it, and they, as last time I hear about it, it's just like they're messing it up. So I would suggest that you use ASD as it has always been available. Okay. And so if you are going to do some work for the government that will require you to strictly adhere to the law, I would strongly suggest that you take the ASD design approach. Generally, they would give you pretty much the same answer because these two design philosophy have the, say, correlation. Okay, so it should not hurt, but you must understand that as well that if you are going to abide by the Thai Building Act, right now, what is only available, what is available is only this ASD. And therefore, you are going to use the design strength that is based on the calculation of nominal strength divided by factor of safety. So that's a building act for you. Okay. So far to this point, is there any question? Any questions, folks? Remember, it's about demand and supply. When you had your mechanics of materials class, you know, it's always like this, right? Check how big your beam has to be so that your flexural stress doesn't exceed this or that number. The major difference between this class and mechanics of materials is that now you get to calculate that stress or strength by yourself using the proper knowledge of how steel is going to behave under any particular loading conditions. So it's only one step further away from what you have had in the mechanics of materials class, in that this time you are going to learn the right side of life calculated based on the suggestions by the spec or the standard. The left side first part begins with the law. You take the load from the law, you figure out the date load, then you perform your analysis to get the forces on your members. So when you know the forces, you will try to predict the strength of your members, how much forces they can actually take. And the prediction methods that you are going to use, you can take from the specs, or you can come up with yourself. And sometimes, you know, it happens that in the real world, when they face a very, very complicated situation, a spec wouldn't help. They have to bring the specimen and test it at the lab to see what happens. Okay. So is there any question? If there isn't any question, we have quite a few minutes left. So I'm just going to start on chapter 1 right away. Any question, folks? No, right? Hey, come on, Mon. Okay, so let's look at chapter 1 right away. So this is like a fundamental of the design. Okay, maybe I should have spoken about this earlier, but you know, I kind of prefer to start off with the concept of the design and the design philosophy. So we are going to get to see this steel shape, you know, building system and load and design philosophy, which are already covered in the first part. Okay. So this is it, you know, in case you don't know, we are going to use the steel, right, in this class. So we're not going to use anything else. It's steel predominantly because this is the steel design class. And I can say that because I'm not the one who covers the timber design part. Okay. So let's say this is the property of the steel. If you haven't seen one before, this is the stress-strain relationship, right? So that's a strain, that's a stress. The first point that you need to know is the yield point right here. This is the actual one, but when we actually design it, we're not going to, you know, pay much attention to the kink. So here's the first yield. Oop. Yeah, first yield, look more like it. So it's all the yield stress of the material, denoted by Fy. And before we reach that point, you know, from 0 up to the first yield, you should know that the stress and strain will be proportional. So that's why you can call the first yield the proportional limit as well. And we can also derive another relationship from the linear relationship between the stress and the strain, and we call that E. Young's modulus, or modulus of elasticity, denoted by ES. Okay, now generally, because I'm so used to it, that's the first reason. And the second is that if you work in this country, you're gonna use the unit kilogram force. Okay, so ES for any steel, regardless of the strength of the steel that you have, this remains one number. That is 2.04 multiplied by 10 to the power of 6 kilogram per square centimeter, or 2 million, roughly. Then change. Even if you use the material with larger Fy, less Fy, this line remains straight with the same slope. Okay. But now you should know that once you, after the first year occurs, and then you keep pulling and pulling and pulling and pulling, yeah, one time your steel member is going to rupture, and right here is where the ultimate strength is. So here is, you can say it's the ultimate tensile strength, or Fu, ultimate. It's yeah, the word is there, so why do I write? So this is Fu. Okay. So far so good, right? Now I believe that we have the grading here. Okay. It's pretty tiny here, so you can look at it here, but the unit here is based on Newton. It's a megapascal kind of thing. So based on this, let me go back to this page and give the numbers to you. Okay. Generally, we use two steel grades in this country, in Thailand. The first one is SS400. It's been there forever. Generally, what we perhaps should have used is SM400, but somehow things got tangled up a long time ago, and they use SS400 instead of SM400. Even though the strength is essentially the same, there's some difference in terms of the welding ability and so, but it should not make that much difference, even though SM400 seems to be, you know, more appropriate in the all-purpose structural work, but SS400 is not going to hurt because it's essentially the same in terms of strength. And somehow people use that until there's no longer SM400. So even though what we should say is, or use is SM400, you cannot indicate SM400 in your drawings or your design because you're not going to be able to find one. But don't worry, it's pretty much the same. But then another one, we have SM520. The number is bigger, so it's stronger, yes. And right now, the price is pretty much the same. So SM520, yes, of course, it's a better choice. But you have to be mindful of some things about them, especially a tiny little bit of a problem called buckling, which we will talk about that in the future. So FY for SS400 is about 2,500. Okay, for SM520, it's 3,700. Now, if you can recall this, see, material. See that? If you know what material you're going to use and then you use the wrong number for the yield and for the ultimate strength, that is bad. Okay, because as an engineer, this is the first thing that you must do in your work. That is, select the material from the beginning and then make sure that you get it correct. Okay, that's the first thing that we do in terms of, say, design engineers, or if you want to be construction engineers, we look at what we call design criteria. Right? Criteria would tell you what material you are going to use. So in the beginning, let's say in terms of design aspect, you must choose the material from the very beginning. And when you choose the material for yourself to use, how can you not know the strength, right? So you must know the strength of your material, because it's a design criteria that you must first set right from the beginning. Okay? So I'm trying to instill this importance into the grading. So whenever you are given the condition to check the structure in the exam or to design something, you must know this. Let's go back here and finish this. So that's the FY. And the FU, SS400 is about 4,050. This is right there in the middle. So I don't take it out because this for the significant figures, this is still counts. It's the third one, okay? And for SM520, it's 5,300. Okay? So that's the material that we are going to use in the class or in real life. Okay? I can tell you one more thing. For the hot roll steel section, you can find both, but typically for the plates, generally we use this for plates. Okay, both of them you can find for hot roll, the H shape, the C shape, the so and so. Okay, for both or for C, I'm not so sure, but the H for sure. C, okay. So, okay, it's 1 minute to 10:20. So I'm not gonna push anymore. I'm just gonna ask you if you have any question. Hello? Any question, folks? Hey! Anyone? Any question? My gosh, am I speaking? Is my microphone on? Is my...
No question, Khab.
Okay, so anyway, I'm gonna stop the record